Hello and good afternoon. Welcome to Yokogawa Test and Measurement Germany, and welcome to a new episode of our popular webinar series on the topic of measurement technology. My name is Markus Ottemeyer, and it's my pleasure to welcome you today and give a short intro before I hand over the floor to our speaker, Sebastian Gryska, our Business Development Manager for Optical Measurement Technology. Now I would like to ask your full attention to our speaker today, over to Sebastian. Sebastian, what's your topic today?
Okay, thank you, Markus.
Welcome.
Hello, I'm Sebastian from Yokogawa, Germany. And today, in our today's webinar, I will introduce our newly developed advanced pulse light measurement mode for our optical spectrum analyzers. In today's webinar, we will have a look at our new measurement function for pulsed light in the mid-infrared region. Because there is a rapid progress in the research, development, and in the commercialization of lasers in the mid-infrared region. These laser sources are increasingly operated with diverse pulse repetition rates, ranging from continuous wave operation to kilohertz range or even sub-kilohertz ranges. Many applications, such as spectroscopy, sensing, microfabrication, and medical treatments, require a precise spectral evaluation across varying pulse conditions. Yokogawa addresses this demand with a new measurement mode designed specially for mid-infrared pulsed light, enabling reliable spectral analysis across diverse pulse conditions. So in today's webinar, we will have a short review on my last webinar where I was explaining our general common functions for pulsed light measurements. Then we have a short look at the already established functions for pulsed light measurements. Afterwards, we will have a look at the challenges coming up when we want to evaluate pulsed sources in the mid-infrared range. One of the challenges coming up in this region is the influence of black body radiation, which will be explained, our countermeasures like lock-in detection, and how it works together with pulsed light. After we have seen the challenges that we are facing, I will introduce our new advanced pulse light measurement mode to face these challenges. Then we will make a live demo showcasing here with our spectral analyzer AQ6375E how this mode in practically usage is used. And at the end, we will have some time for your questions, and I hope I can give some good answers. In our last webinar, I was giving a detailed explanation about all of our functions for measuring pulsed light sources. This webinar can be still downloaded or watched when you go to our website to tmi.yokogawa.com/de/library. If you want to access this webinar, you have to visit the German Yokogawa website. In my last webinar, I was introducing and explaining our general functions for pulsed light measurement, such as the peak hold mode, the external trigger mode, and the gate mode. And I was explaining for what kind of operation modes of the laser and what repetition frequency which mode is usable. And we have seen that for repetition rates larger than 10 megahertz, these are like continuous lasers for our instrument. If we are coming to lower repetition rates in the range between 10 megahertz and around 500 hertz, we can cover these pulse rates with different settings, with different sensitivity settings, and these can also be measured in the time average spectrum. If we are coming to lower frequencies, then we offer the peak hold mode, an external trigger mode, and even a gate sampling mode, which is also usable for irregular pulses and bursts. In our common pulse light measurement settings, we were facing some limitations that were explained in the last webinar. One of the most important limitations that we are also addressing right now with our new advanced pulse light measurement mode is that the chop mode or the high dynamic mode was not available for the common pulse light measurement functions. But due to the growing use of mid-infrared pulsed lasers, we saw the need to face these challenges. One challenge is that the performance in the mid-infrared region is constrained by the infrared background effects, such as blackbody radiation. And with our common settings, we have already a long time established, we are a little bit limited in the handling of low repetition rates combined with the compensation of blackbody radiation. So first, let's have a look at the blackbody radiation that is influencing our measurements. The blackbody radiation gets important when we are coming to regions above 2 micrometers. Can you see my mouse? No, probably not. Yes? Okay. Here we see when the blackbody radiation is coming up. And here around 300 Kelvin, which is around the common environmental temperature, we see the effects of the blackbody radiation are getting important, especially when we are going to regions above 2 micrometer wavelength. The challenges with this blackbody radiation is that this blackbody radiation is fluctuating with temperature changes. As you can see from the graph, that it's not a constant line, but it is developing with temperature. These influences are then unfortunately superimposed on the laser spectrum. And another challenge is when these blackbody radiation changes during the measurement because of a temperature drift, also this blackbody radiation is fluctuating, which then can lead to over or under correction. So without special countermeasures in this wavelength region, there may come up considerable effects on the optical spectrum analysis. The blackbody radiation changes in intensity and spectrum with temperature fluctuations, introducing noise into the measurement. As this blackbody radiation is fluctuating with temperature changes, and to compensate these, a frequent background correction is required to make pulse light measurement, which makes the pulse light measurement particularly difficult, because in this regions measurements can take a little bit longer, and we may face the influences of changing temperatures. To compensate the influences of the blackbody radiation, a common technique used is the lock-in detection. To compensate the influence of blackbody radiations, all Yokogawa lasers covering the wavelength range above 2 micrometers are equipped with a lock-in detection. On our instrument, we call it the chop or the high dynamic mode. The principle of locked-in detection is that weak optical signals can be measured by modulating the input light source at a specific frequency. To modulate this input light, a chopper wheel is used. The lock-in amplifier then calculates the detector signal with the reference frequency, extracting only that component which is important for us, while filtering out the noise at other frequencies. With these techniques, we can achieve a much higher measurement dynamic than without, what you can see on the graphs below. So the offset that was introduced to the blackbody radiation is compensated, and we can detect our signal with a high measurement dynamic. One of the challenge that is coming up with a lock-in detection is when the pulse repetition rate is getting low and when it's coming close to the frequency of the chopper wheel. And if we are facing these challenges and the chopper frequency and the pulse slide frequency are interfering, then also a measurement error may occur and we will not get a clear spectral representation of our signal. To overcome these challenges, Yokogawa has introduced the new advanced pulse slide measurement mode. This new function was introduced to successfully overcome the key challenges of mid-infrared pulse slide spectrum measurement. And with this new technique, we can mitigate the influence of infrared radiation, and we are able to expand the measurable range of pulse slide characteristics, just as pulse width and repetition period. Since the intensity and spectrum of infrared radiation constantly fluctuates with temperature changes, background correction must be performed at intervals shorter than the time it takes for the infrared radiation spectrum to change. Our new advanced pulse slide measurement mode is dividing the measurement span into different segments. This results in a reduced measurement time per each segment. And then the background correction can be performed for each second on time. With this technique, the influence of fluctuating blackbody radiation caused by temperature changes is effectively suppressed. And as we are doing it frequently and in shorter periods, then the temperature need takes to change, even over or under correction of the signal is prevented. Here we can see the difference between our conventional measurement modes and our new advanced pulse slide measurement mode. In conventional measurement, an offset due to the infrared radiation is superimposed on the waveform, and also measurement errors can occur. In the APLM mode, these effects are reduced that the laser spectrum can be visualized over a wide measurement dynamic range. With now having the capability of doing proper evaluations of pulse sources over a broader range of repetition rates and duty cycles, this greatly contributes to the advancing of the performance of lasers operating in the mid-infrared range. This new measurement mode was introduced with our latest model, the AQ6377E, which is covering a wavelength range from 1900 nanometer up to 5.5 micrometer. But this mode was also introduced for our other spectrum analyzer models covering the mid-infrared, our AQ6375E, our 2 micrometer model covering the range from 1000 up to 2500 nanometers, and our AQ6376E, covering a range from 1500 up to 3400 nanometers. This new firmware function is available for all models of AQ6375E and 6376E. All models of AQ6377E are already equipped with this new measurement mode. The new firmware containing these new functions can be downloaded from our portal. So please visit myportal.yokogawa.com, get connected to us, and always stay informed about the recent firmware updates, drivers, or software updates. Now we will have a short look at the possible setting and the setup procedure for the advanced pulse light measurement mode. This mode can be found with our common settings under the pulse light measurement. And we have some additional settings for this new mode. The important settings that can be done are first selecting the sensitivity. In our already established pulse light functions, we only had the capability of using the sensitivities up to the mid sensitivity, but all sensitivities using the lock-in detections were not available for the pulse light measurement. This is now possible. So you can set a required sensitivity starting from a lower sensitivities like in the normal sensitivity mode, and you can also select higher sensitivities like high 1, high 2, or high 3. Then you have to select your sampling interval, which is determined by your pulse repetition frequency. And the sampling interval, the hold time for the sampling interval should always be longer than the repetition period, so that we always can detect the peak power and can measure the input light properly. And a new setting now is the segment points, because we separated the whole measurement into many different segments. Here we have the ability to, on the one hand, use the automatic settings, which are designed that for each segment, the measurement time is not longer than about 1 minute. Or you can also set these segment points according to your needs manually. And now that I have explained a little bit this new mode, we will have a look at the practical function and how it's really working in real life. So now I will change the camera. Okay, now I switched the camera and you can see the screen of our AQ6375E. Today I will be working with a DFB laser working around 1300 nanometers. So in this range, the influences of blackbody radiation will not be present, but we can showcase the functionality of this new measurement mode. For the beginning, I will start with a laser source, which is operated at a repetition frequency of 10 kilohertz. 10 kilohertz is a repetition frequency that, if we are selecting appropriate settings on our instrument, can always almost be measured like a continuous wave. So the laser is already enabled. It is working at a frequency of 10 kilohertz. And now we just make a span and see the spectral representation of this signal. As we see, if we are operating at 10 kilohertz, we get a clear spectral representation of our signal. And also, as we are experienced and as we have already known, we can now also switch to the high dynamic mode or the chop mode to improve our measurement dynamic. Now I make a new measurement. And comparing the two measurement traces, you can see enabling the high dynamic mode or the chop mode is improving the sensitivity and the measurable range, power range of our signal. As we are now operating at a quite high repetition frequency of about 10 kilohertz, the measurements at this frequency makes no problems. But now I will reduce the repetition frequency of our laser source to 1 kilohertz. In the 1 kilohertz region, it already may get a little bit difficult to make a proper spectral measurement. So we now first try again with sensitivity setting mid and make a measurement of these that 1 kilohertz modulated laser. And we are seeing now that we are getting a strong interference of our signal due to the repetition rate and the update rate of our signal, which makes it impossible to detect the spectrum of this laser source. Even if we increase the sensitivity, then due to the longer integration time, we can measure this laser signal and get almost clear spectral representation of the signal. And we can also use the high dynamic mode to improve the measurable dynamic range. But we already see some distortions due to the pulsed frequency of our laser source. To achieve a good measurement result, even with this repetition rate, we can now use our pulse slide measurement function. And I will start with a common function that was we have already a long time implemented. And this is also the peak hold mode. In the peak hold mode, we set a specific time for each sampling point to give it enough time to detect the power of the signal. And when we now switch to the peak hold mode, we just have to set the peak hold time. And the experienced user will already see the first difference. With our common pulse slide measurement functions, the chop mode or the high dynamic mode was not available for the peak hold mode. Now there was no influence, and we were able to switch also to the high dynamic mode even when the peak hold mode for pulse slide measurement function is enabled. So this is the first strong improvement, that now, even if you are using common measurement modes, the high dynamic mode can be enabled and the chop mode can be used for peak hold mode with various repetition rates. Now we make a new measurement with our set peak hold time and a medium sensitivity, and we will see how the spectral representation of our signal will look like. And we can see in the peak hold mode, the measurement of the repetition rate of this laser is absolutely no problem, and we are getting a really clear spectrum without any distortions. So now I stop the measurement to save some time. And one big advancement is that we now in the peak hold mode also can select the high dynamic mode. And if we now do a new measurement, we see we can even improve the measurement dynamic range of our signal and get a much more clear and higher dynamic measurement range. And our signal is also still represented clearly, and we are getting a clear and distortion-free spectrum of our signal. You see, the peak power of the signal is not changing. The changes in the sensitivity setting only changed the detectable power levels and was increasing our dynamic range for this measurement. Now I will decrease the repetition rate of this signal even further, and we will go to a repetition rate of only 100 Hertz now. For this, now I changed the repetition frequency of this laser that we are using here to 100 Hertz. And we are making a new measurement and want to have a look how it is looking like. The pulse light measurement mode is still set to peak hold, and we have the same peak hold time like before. As we see, we also get a clear spectral shape of our signal without any relevant distortions. Now I will stop it. Now I will change the sensitivity to high 1, to a mode which is also using our lock-in detection and is also called our high dynamic mode. As we are now just increasing the integration time for each measurement point, we would expect no decrease of the spectral shape of the signal. But if we do a measurement, we see we have increased our measurable dynamic range. But when we are now coming to the peak power of the signal, we are seeing strong distortions of the spectral representation of the signal. These distortions are caused by the influences of the lock-in detection and the frequency of the chopper wheel. To overcome these challenges and to make it possible for our spectrum analyzers to even clearly analyze laser signals with low repetition rates, we now will test what the new advanced pulse light measurement mode brings, what advantages it will bring. We now have here also the setting of advanced pulse mode together with the common pulse light settings, and now we go to the settings of for the advanced pulse light measurement mode. We have a sensitivity high 1. We set the sampling interval according to our repetition frequency of our laser source, that we get a good detection of all the peaks. And now the segment points are automatically set to 20. This means for our whole measurement range, the instrument is now set by its automatic algorithm to an overall number of sampling points of 468. This new advanced pulse light measurement mode now divided this whole measurement span in single parts, where each part is containing only 20 sampling points, which now makes it possible to apply the background correction of the infrared radiation step by step for each segment point. And now we will make a new measurement. You now can see the spectrum is scanned for each segment, and then for each segment the background correction of the infrared radiation is performed. And as you can see now, with these new functions, we now can even clearly analyze laser sources with repetition range that may interfere with the frequency of the lock-in detection. And with this new mode, we now can measure also mid-infrared laser sources over a very broad range of repetition rates and pulse cycles and duty cycles. Another big advantage of this new advanced pulse light measurement mode is that this can also be applied to medium sensitivities, which before were just performed without extra background correction. And now even if we do longer measurements with lower sensitivities, also a proper background correction also for fluctuating temperatures can be applied. And this was our new advanced pulse light measurement mode. If you have any questions about this mode or about any our analyzers, please put your questions in the chat right now and we will answer them directly. One question. Okay, we will come to the questions. Yes, this function is available as a firmware update, but only for AQ6375E and 6376E. For these two models, this new function can be implemented by downloading the newest firmware. To get the newest firmware, go to portal.yokogawa.com, register, and then you can download the firmware and install it on your device. If you want to have some price information about this model or our other models covering the mid-infrared, just contact your next Yokogawa dealer. To find your next Yokogawa dealer, just go to tmi.yokogawa.com, select your appropriate region, and then you will get to the contact person responsible for you. If you want to know more about our mid-infrared models or anything else, feel free to contact us. Meet us, for example, at the Laser Congress in Aachen in the end of April, or in May in Munich at the ONDM conference, in September at the ECOC in Malaga, and in the end of the year in November at the Electronica in Munich. Thank you for attending today's webinars. And if you are interested in any other measurement functions of Yokogawa, just write the topic into the chat or contact us for what is interesting for you. And we will take this in consideration for our next webinar. Thank you for today. I'm looking forward to our next webinar and have a nice afternoon. Goodbye.